I have a fun question. So that was me being curmudgeonly. Hopefully that's motivating you, not trying to scare you. Imagine we have a situation. Imagine we have a situation like this. You have a gun. Okay, some kind of dart gun or something. There's going to be a projectile coming out of here. Right? I'm going to launch this projectile at some speed, v0. Okay, so there's going to be a projectile. At the instant that the bullet comes out of the gun or the projectile launcher or whatever you want to call it, let's say over here, this is a terrible looking duck. That's terrible, but let's put a nice eyeball. Okay, let's say we have a duck. And for some reason, this duck is hanging on a branch. Kind of like you see over there. See the duck? I'll show you on Zoom in just a second. And the idea is, when this duck hears the bullet come out the gun, the duck gets shot and lets go of the branch that it's hanging on to. So when I was in school, I think it was a blowgun and a monkey. So you get, all right, or whatever. In any event, this is the idea. At the instant the bullet comes out of the gun, the duck is going to let go of the branch. Now let's go try and get a visual on what this looks like. Whoops, wrong way. There's that duck. And this arrow back here, if we're sitting on Zoom, this is just an arrow stuck on the whiteboard somewhere. So now look at this thing here, and I don't know if you can see this very well. Right up here is my projectile launcher. And I want to show you how this works. So what I'm going to do is if I hit the active button, the idea is this little sensor that's sitting here, if I break the beam, watch what happens to the duck. So the idea will be at the instant the bullet comes out of the gun, that's going to trigger this beam and cause the duck to fall down. So far, so good. And now, in order to make this, I don't know, stand out better, we have yellow spheres. So maybe I'll get rid of the duck and put a target up here instead. Okay, just so that you can actually see the yellow ball hit the thing. And we can shoot the duck later if we want. But the idea is that. Let's go back to this now. That's the concept. I have a question for you. Where should you aim to hit the duck? Should you aim directly at it, above it, or below it? So take a second to talk to your neighbor. We want to hit the duck, and we want to know which way to aim. Should I aim below the duck? Talk to your neighbor. At the duck directly, or above the duck? Take a second to talk it through. We're going to shoot this, so do I need to shoot above?
Yeah.
Depends on how fast the projectile flies. But however, if it goes at a really rapid pace,
Give me another 30 seconds. Keep talking. Thank you.
actually, this would have to do on the projectile itself.
Although actually, I heard
Last week it was going to land in the basket. This week, question.
All right. And so one of the things that we want to do, and the reason I ask these questions, is the educational research indicates that if you commit to a guess, even if you're wrong, you generally will tend to remember the explanation more. So don't be shy. Let's just go through it. Okay, so take a guess. It's okay to be right. It's okay to be wrong. We don't care about that. All we care about is being engaged. So at this point, how many think you need to aim below the duck? Raise your hand. Just gotta keep it up. Okay, got a couple. How many think you need to aim at the duck? Got a few, most. And then how many think you need to add above the duck? Got a couple. All right. So notice this is not an intuitive problem. Do you agree? There's not some obvious answer right away. My claim is we should actually aim at the duck. Now, when we do this, here's how I want you to think about this. Let's first imagine a world with no gravity. If there was no gravity, and if we were in deep outer space, when the duck lets go of the branch, what will happen to the duck? It's just going to magically float because we're in a magical world with no gravity. Okay? Do you agree that if you aim straight at it, the bullet would hit the duck? Okay. Now, let's say we turn gravity back on. When the duck lets go of the branch, what would the duck do? Fall down, right? What equation could be used to describe the vertical displacement of the duck? What does vertical displacement mean? What symbol do we usually use for vertical? Delta y. That's going to be 1/2 a sub yt squared. Right? But what's a sub y? What is it?
Negative G.
Negative g. Excellent. You remember the negative. Okay. Now, let's think about this one, the bullet. Does anybody have any equations for the displacement of the bullet in free fall?
I think that's two. Right?
What's that?
It's in the y direction and also that the x direction.
There would be. There's one for the x direction and for the y direction. Agreed?
Yeah.
Give me either one of these equations. What would it be for this one, for the bullet?
Acceleration times.
The initial t plus 1/2 a sub x t squared. The initial y times t. Well, it was just the same equation, is it not?
Yeah.
It's our standard. Let me ask you this. Is the acceleration after the ball leaves the gun? After the ball leaves the gun, not while it's in the gun. After it leaves the gun, we typically ignore air resistance. There's only one force, gravity. It's a free fall problem. Is it constant acceleration after it leaves the gun? Yes. What is the acceleration components, or what are they?
X,
0 in the
X. Negative G.
The idea is this. When it leaves, it's going to fall below the straight line path. This part right here is V0 sine theta t. This is the part that describes this. That is, let me rephrase. This is like that. The idea is if there's no gravity, this term would be gone. The displacement would be V0 sine theta t. You add back in the gravity, it comes right back down just like the duck. Yes.
Then that means wouldn't it be a V sine theta times t minus 1/2
Yes,
a.
absolutely. So we could rewrite this right here. like that, right? The idea is this is the straight line path. You aim straight at it. If you turn on gravity, this one falls below its straight line path by this. This one falls below its straight line path by this. Well, it had no straight line path, so it just falls. Isn't that crazy? Do we think this is true? Can we prove it? This is one more case of saying the X motion and Y motion are independent. I don't know if you caught that. That's what I'm trying to. All right, let's take a look. I need a student to come up here real quick. Somebody that's got to aim this thing. I want you to verify it. All you have to do is look through this gun. The sooner we get it done, the sooner we can do more problems. So, somebody just come up. Thanks, boss. I appreciate it. All right. So the idea here is, I think I've already aimed it correctly. So what I want to do is this. I'm going to turn this to inactive. That deactivates the photo gate, and then I'm going to put this sight on here. And so here's a little sight. So you can see there's a little hole in the middle. There's another one right here. And I want you to make sure I didn't screw this up. Just try and line it up so you're looking through both holes simultaneously. And hopefully you're seeing right here in the center of the target approximately.
Yeah,
Pretty close?
pretty close, yeah.
All right, all right. Now let's go ahead and try this. You want to pull the trigger for me? All you have to do is just lift straight up. And then you're probably going to stand over here on this side so the camera. Yeah, there we go. Give me a second. Remember, it's inactive. Don't do anything yet. Now I have to activate that sensor. So now it should operate. And then, okay, so let's just, yeah. There, let's do this. Let's give him a drum roll, everybody. Just okay, okay, yeah, okay. That's like, that's, yeah, thank you. Oh, it works. All right, let's give her a round of applause here. Okay. Now, wait a second. I could have, oh, you're good. I could have sworn I heard some students saying something about, doesn't the speed matter? What do you think? If we do this again, but shoot it more slowly, well, if anything, it will be different. Take a second, discuss. Let's say I shoot, right? I shot that at max speed. What if I shoot it more slowly?
It's gonna yes. But do consider that it's going to cover the part of the ground. What must come up must come down. So eventually it's going to reach a maximum height and then after this decline from there simulate onto a certain point, whether or not it's gonna hit it.
Yeah, I think it's weird.
About the semi ball.
Okay, let's take a second to look over here. What, if anything, is going to be different? So first, let me ask this. If we fire it at a slower speed, will everything be exactly the same? What's your gut tell you? Will every aspect of this problem be identical if we shoot it at a different speed? No, what will be different? Okay, if V initial is smaller, what should happen?
For the dot.
Do you agree it's going to take longer to get there? So what should happen to how far the duck goes? Will the distance the duck falls be the same, or will the duck fall more, or will it fall less? More. So the main difference here is the duck is going to fall and you'll hit lower, and it'll take a little bit longer. But this shouldn't change where we aim. Do you agree? The physics is still the same as far as that goes. So what changes is the time of flight and the impact location, but it doesn't change the fact that the amount the duck falls is equivalent to the amount. So let's try it one more time. All right. Yeah, sure. I think I loaded it, so I put this on the medium speed. So yeah, so let's go ahead and do it. I think you're ready. Is everybody ready? You don't need a drum roll this time. Okay, I thought it was good. I forgot to hit activate. Remember, I have to activate the sensor. Great job. Let's give him a, yeah, load it again. Sorry about that. So
We can't see over
before
here
I
in
had
Zoom.
you on long range. Now we're going to medium range. So hopefully it still works. Okay, now I got to hit the active. Now it should operate. Sorry about that. Okay, ready?
Yeah.
Oh, question?
Is the camera?
Thank you. I forgot the camera. Thanks. That's good. Oops, wrong way. Oops. Thank you for bringing that up. Yeah, did I not hear you there? Oh, I didn't hear you. Maybe I turned the volume down. I didn't hear you there. That's weird. I don't have the mute button hit. Try it again, Alan.
You hear me all right?
No, I don't hear you.
Are the speakers like this?
All right, we'll worry about, so you may have, okay, I guess I can't hear you. We'll worry about that in a minute. Let's go ahead and get the shot right. Okay, now, here we go. Hopefully you can see it on Zoom. All right, he's gonna shoot it at slower speed. Let's do it. Still hits, it just hits slower. Now, obviously, this is gonna break down at some point. What happens if you shoot so slowly, the ball never hits that? Well, okay, that's a problem. But yeah, all right, let's give him a round of applause. Okay, those of you on Zoom, can you try one more time? Alan, if you're speaking, I can't hear you here.
Could you hear me now?
Are you trying to talk? Let me see if the volume got turned down on this one. Huh.
Could it be the speakers not that for this computer?
I don't know. It's always something. I had to reset the camera earlier. You can hear us fine, so yeah, we'll see if we can figure it out on the break. So yeah, I'll try and be active on checking the chat, but Alan, you know me, I'm sometimes bad at that. So, all right. Okay, if you have questions on Zoom, I apologize, and I don't know why the mic's not working right now. Okay, so yeah, if you do have questions on Zoom, you can ask Alan as well. Alan knows all this. All right, so that was kind of a fun warm-up, right? Now, I want to try another question, all right? And I want to look at the next question in the book, 4.23. So take a second to look at 4.23. I love that question. When I was at your age in school, they actually brought in real rifles and shot stuff.
No way.
Yeah, I know. Think about that in the modern era. That's just like nobody's going to bring guns to school these days.
Like airsoft rifles or like?
Oh yeah, just I think they were shooting pellets or something. It's pretty wild. Yeah, but I mean, there's a different era. Shooting guns in class and doing the calculations. Kind of an old school way of learning. Oh. Okay. One of my favorites. Suppose you have to design a ski slope. Perfect timing with the Winter Olympics, because when else does anyone ever think about ski slopes? Let's say you're a ski jumper here. Okay, and you're going to come flying off here with some speed, V naught, at some angle, theta. And then I probably need to draw this ski slope a little bit better here. You can imagine this ski slope, ski jumper might land over here like this and be moving this direction at the end of their flight. And I'm going to call this angle, I think in the homework problem, I called it psi. Looks like a saguaro cactus. Just draw a letter U and then draw a line through it for psi. Draw a letter U, line through it, psi. And I did that because very oftentimes, this is a standard question in many books. Most books like to call the angle of the slope of the mountain phi. Okay. And our goal here is the following. Part A, we want to show downslope range is L equals some big ugly equation here. I'm going to write it down. 2 V squared cosine, I got to be careful here, thetas and phis. With that downslope range should have a V0 on it. Oh, wait, the initial velocity was V, not V0. Is that what I called it? I apologize. Cosine squared of phi on the basement. All right. Yes. So we have this goal. We want to show that the downslope range is this. To be clear, what I mean by downslope range, I mean this. The range of the projectile down here. So that's what I mean by L. The length that they go down the slope. So just to color code this, I'll put an L here. Is that clear? Furthermore, this is really what I want to do with part B. Right? What launch angle will give the maximum downslope range? Imagine you are working for the Olympics and your job is to make the most exciting Olympics ever. My claim is, right, you could design the angle at which they jump to make sure the jumps go as far as possible. People are breaking all kinds of records.
And boats.
Now, what's that?
And boats.
And what?
And boats.
Well, yeah, so it's an interesting thing here is the angles actually matter a lot. And there was actually a lawsuit a couple of years ago for some ski slope designer that didn't take into account the angle of impact. And so we're going to completely ignore that. You know what else I'm going to feel like ignoring? Air resistance. Is that realistic for a ski slope problem? No. Have you seen how they fly? They're literally flying as they go down the slope, right? So we're going to ignore that so that the problem is doable in an hour. So it's a completely made up problem. But it gives us an idea of how we might approach a real world problem. We're first going to solve the problem without air resistance. And then once we do that, we can try and add in air resistance if we're crazy. So far, so good? All right. Well, these are our goals. What's something we could do here? List some stuff. And in fact, I'm going to make a special spot right here. I want to list my givens. So what are the parameters that we're going to think for? Sometimes these are the things that are known. V, theta, and phi, and I think G is impact. Those are things we know. Notice how critical it is to write these angles differently and be consistent. Both of them are going to show up in the answer. We've got to be very detail oriented. So the claim is, right, if we have a given V, theta, phi, and G, we should be able to figure out that this is true. Now, a common mistake that students make at this level is when they say, show this is true, they'll start with this equation. What a physicist means when they say that, basically means prove that that's true. So they're essentially telling you, I suspect you're going to get this answer. I'm solving for L. Show that when you do your normal work, you get this answer. So don't start here, end there. Is that okay?
Yeah.
Okay. Now somebody said, what can I do? First thing. I've got a picture. Equations. What else do we usually do just before the equations? The list of knowns and unknowns. Okay. So there's going to be a delta X, delta Y, the initial x, the initial y, a sub x, a sub y, the final x, the final y, and time 1, 2, 3, 4, 5, 6, 7, 8. Did I get it? 7, 8, 9. Got it. Now, normally we would make two separate lists, but I'm on Zoom and I'm running out of whiteboard, so that's why I got to do this. Sorry. Okay. All right. Anybody want to tell me any of these things? What's that? For which one? Yeah, okay. So he's saying, look, I'm looking for L. I want to get L involved. I think you're probably drawing this triangle in your mind. Is that right?
Yeah.
And he's saying, look, I know this side is L cosine phi. You agree? Outstanding. L cosine of phi. Again, this is sort of a, going back to what we did 2 weeks ago and last week, we're trying to take something in terms of delta x and rewrite that in terms of the parameters for this particular. So we're taking an arbitrary unknown delta x and rewriting it in terms of the parameters we care about. Okay. Probably did some SOHCAHTOA on that. Okay, what's delta y? Did I hear L sine theta?
Yep.
That's not right.
Sine phi.
L sine phi is not right. Just remind me, which way is up for most of you? Isn't usually that way up? What's the change in y? Did it go up or down?
Oh.
We start here, we end there.
Negative.
The size is L sine phi. That looks terrible. The size of it is L, but it goes downwards. It's negative L sine phi. Did that make any sense at all, what I was trying to say? Most of you are probably not rotating the coordinate system upside down. I can tell that because what is AY?
Negative.
Yeah, so if you can't have it both ways, you can't say, well, gravity's pulling me down, but I'm going upwards. That doesn't work. That's why I'm trying to, okay. Everybody cool with that? All right, what's AX? All right, what's the initial X? Yeah, it's the initial cosine theta, right? You're right, it's got to relate to this. I think this one, some of you might have called it V0 because I initially wrote V0. I'm just trying to match the problem statement. And I think in this one I said the initial speed was V. Okay, what's the initial Y? Don't overthink it. V sine theta. Do I need to worry about minus signs for this one? No, because it's going up. Do you know the final velocity in the X? What is it? Yeah, how do you know that? Yeah, careful, it's a special constant, 0. Yeah, you got the right idea. If AX is 0, initial and final X are the same. So I'll just write V initial X because I'm lazy. How about V final Y? Do you know that?
That's
I don't know it.
wonder.
That would be over here, right? This is V final X and V final Y. We know that V final X is not going to change from the initial state, but the up and down velocity is definitely going to change because gravity is affecting it up and down. Yes?
How do you figure out with kinematic equations?
Maybe. So just because we don't know it right now, it doesn't mean it can't be determined. And in fact, I bet you could determine this. And you can figure out the impact speed and determine whether or not people are going to break their bones. Right? So there is a purpose to figure that out. We're not doing that one today. Time? Did I tell you the time? Good. So far, so good? What's next? Now we get our equations. Okay, so I'm going to go over to the other whiteboard on Zoom here. Oops, I'll get out of the way. Any questions about this before we go on? If you think you can get it faster than me, go. No, I need maximum whiteboard here, so I'm trying to get it just right. Good. All right, so. Let's start with this equation. The delta x equation. Do you agree the a sub x part should drop out because a equals 0? If you recall, this was the only useful equation for the x for a standard projectile. This is a standard projectile problem. Wait, so out of this, don't we get something that looks like, what was it, L cosine of phi equals V cosine theta t. Is that right? Yes. All right. I'm just going to check. I know this, this, and this. Those are knowns. What is the thing that ultimately we're trying to find? In part A, what were we trying to find? The L equation. So I know if I just solve this for L, I still have an unknown. That's not good enough. Agreed? So what might it, okay, maybe we should write some more equations, all right?
Time.
What's that?
We find time and then plug in.
We could find the time, and that turns out is going to be very useful. We could solve this for t really quick. Now, I tend to screw this up, so make sure I don't flip it. I actually screwed it up in the earlier class today. It's like the one I always flip. So I'm going to check. T should equal L cos over V cos. And I got to make sure I get the right thetas and phis. Okay. That's looking good. So far, so good. Now we could use the delta y equation for x. Or maybe we could use the v final y . Now, in this case, I'm just going to do a quick check. This is kind of what I'm looking for because that's got an L sine phi with a minus sign in it. I know this, but I don't know this. That doesn't necessarily help me right away. I could take that time up there and plug it into here. Because in theory, we kind of know this, but not really. I know this, but I don't know this. So you could say, well, maybe I could try and use this time in here, figure out b final y, and then plug it into here and solve for that. That might work. Still not happy with that. Well, I do have an equation for this, and I know this, and I have that equation for this, and I know this, and I have an equation for this, kind of ish, right? I think the easiest way might be to use the first equation. Now, if you weren't sure, like I said, somebody was asking, could I get b final y? Yeah, you could, but remember, that's going to then be in terms of the unknown thing L. So I think the first equation is probably the way to go here. All right. You don't have to do this step of kind of thinking through, but for me, it kind of helps. I'm just kind of thinking through. I think this might have a decent chance of success. What was delta y?
Negative sign.
Negative L sine phi. The initial y is v sine theta. I'll just leave this at t for right now. And I'm thinking this is looking good. If I use this equation right here for t, I'm going to see everything's got an L in it, and maybe I could do some work. Right? The only unknowns we have are T and L. Well, if you look at these two equations, this equation in a box and that equation in a box, think about it. We have two equations, two unknowns. Known, 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 known. So two equations, the same two unknowns. This is going to get the job done. What do you think, though? We're going to have to do the quadratic formula to solve for L. When I plug in here, are you going to get an L squared? So do you think we're going to have to do the quadratic formula? Hopefully not. This one's going to have an L as well. We'll all have an L. One of the L's should cancel. Okay, if you think you can beat me, go for it. You can race. I'm going to start working it out. If you want to watch me, that's fine. If you want to not watch me and try and race, if you want to use the solution, whatever works for you. Let's start rocking. Okay. Sine theta. Many different correct ways to get there. I'm just going to plug in that T. Here's a tip. To make this work easier, I recommend this. You could change sine theta over cosine theta into tangent, but don't. That's my advice. That'll save you a little time later. Seriously. Just leave it sine theta over cosine theta. Is that looking good? Very good. Good. All right. And here's what I was saying. Every term is going to have an L in it. This one an L squared. We could factor all those out and cancel one of the L's, and there'll be one left in this term. I'm going to do that right now. I guess I can cancel the V right here. Do you agree?
Yep.
I'm going to do that. And I'm just going to rewrite so I don't get lost. I like to let the paper do the work. Just because you can do it in your head doesn't mean you should. A lot of times, that's when you start making mistakes. You're faster if you do it on paper most of the time. Because you'll accidentally change a theta to a phi or something like that. So forget a square. So I'm just taking one step at a time, trying not to do too much work. Now I can divide each term by L. Right? Whatever you do to one term, you must do to all terms. Now I see these two L's cancel. Are there different orders to do this? Sure. I'm going to bring this up here so I can work. I'm going to do this. You know what? I'm going to rewrite so I don't get lost. That's what I'm going to do. Because when you're moving it up like this, that's when you might get lost. I'm going to make this look a little prettier here. Notice what I did here on this last term. I wrote all the other terms exactly the same, didn't do anything. But this one, I just moved the L to the end because I know we're trying to isolate L, right? This is just a style. It's not necessarily the best style. It's a style. There's about 6 others that are equally fast. I'm going to move this to the other side because I like to have the thing that I'm solving for on the left side. And I'm going to move this over here, and that makes everything positive. You see that? Bring this to the other side. by adding all that crap. This the other side by adding all that. So far, so good, just moving stuff around. Here's why I told you not to cancel this cosine in the basement. I'm going to multiply every term here. Let's see here, let me go. You still read the subscripts on Zoom there? Are you still good with the subscripts? Alan, I'm looking at the chat. Okay, gotcha. Thanks. All right. What I want to do is I want to multiply all of them by the inverse of that, which was 2v squared cos squared theta div g cos squared b. Right? When I do that, I'm basically multiplying by the reciprocal of this crap. When I do that, I solve for L. That was our goal. And now I'm just going to write it here. And now I can distribute it through. When I do this, this is a good time to actually check the answer. Part of the reason they do this in a physics book is for this step right here. I want to show you something here. Sure.
Even if we wanted to, we couldn't cancel out the cosine because it has different.
Yeah, you can't cancel out cosine theta with cosine phi. You're absolutely right. So we can't cancel this cosine theta with that cosine phi.
Right.
Now, what I was saying is you don't want to group the sine theta over cosine theta and set that equal to tangent. That's true.
Okay.
But I don't know if you can see here when I cross multiply, you see we're going to start canceling.
Yeah.
That's why I was trying to save you time with that. Because then you'd have to unconvert the tangent.
Would it be better just to do that stuff at the edge if you can?
Every problem's different.
Right.
Yeah, how about I leave it? Yeah, that's not a very satisfying. One of the things that the reason I have you do lots of homework in a physics class is basically each problem you learn about one thing, hopefully, right? And so then it takes a lot of time to learn all the tricks and learn like, oh, in this scenario, this is best. In this, that's just experience. Yeah, good. Now look, I wanted to point this out. In this equation, it's telling you what prefactor should be sitting out front. And I can see I got a 2v squared cosine to the 1. Look at that. That's not cosine squared. That's cosine to the 1 on top, cosine squared on bottom. So I'm going to try and use that to model this. I'm going to set up my prefactor 2v squared cosine of theta over g cosine squared of phi. There's still another cosine theta, right? The idea is I'm going to bring this cosine theta inside those parentheses. And when I do that, it's going to appear on each term. Let me get back to the board here. And then notice I'm going to have a cosine theta here that I brought in. Are you guys able to follow this okay or not? Yeah, I'll tell you what, give me a second. Thumbs up, thumbs down if you're able to follow. It's okay if you can't. Okay, for the most part, people are getting most of this. Okay, take a look. Sweet. What do you think this is? Which one? I'll give you a hint. I feel like maybe if I just look at the very bottom of page 76, there might be some trig identities to help you out. Take a look at the bottom of that page. This is like the letter A. This is like the letter B. This is like the letter A. No, that's like the letter B. This is like the letter A. So anywhere I see a B, you can think of that as B in the trig identity. Anywhere you see a theta, do you agree this is sine theta plus B? Are you okay with that from the trig identity? All right. So I'm just going to write that final result here somewhere. Like this. If you have trouble seeing that, or if you're starting to freak out because you're like, oh my gosh, I have to know trig identities, don't worry. If there was a trig identity you had to use, I would usually give that to you on the test. Furthermore, I know I have no trouble failing students without trig identity. So I don't need to put any trig identities. I'll try and keep it simple. And you watch. It's like people will still have trouble with the simple stuff. All right.
What about the unit zero? I mean, the unit circle. Sorry.
What about it? I recommend knowing it, but right, you got to calculate it.
Yeah.
Yeah, right. There's right at this point, right? I was hoping everybody would know everything, but let's face it, you don't. Right? You're students, you're still learning. By the time you get through your second or third physics course, a lot of these things will start to be memorized. This is your first one. You shouldn't have all this stuff memorized. You don't have these trig identities. I don't expect you to. That's what we got calculators and tables for. Okay.
Awesome.
Yeah. So let's not worry about that stuff. All right. Cool. How can I check this result? Give me one way to check it.
Give us an example.
Well, what do you mean? Yeah, that's true. That's one way to check it. Check the answer that I gave. Absolutely. What's another way to check it? Like, let's say we didn't have the answer. You're absolutely right. That's the best way. Good, it works. What's another way we could confirm and feel good about this? True. If we plugged in numbers, we'd have to actually do the experiment. Huh. Maybe that's what this giant ski slope's doing down here. I don't want to do that yet. So we're going to do the experiment in a minute. Okay. What's another way we could check this result? Yeah. We could check some units. All right. So let's check. What are the units of sine theta? Nothing, right? How about cos? So what are the units of all this? Yeah, velocity squared over g, which equals meters squared per second squared times second squared over meters, which is meters. That's a length. That's looking good. What's another way we could check it? That looks good. I got one for you. This is one that might not be obvious to you now. Part of the reason we're doing this problem is to help you learn this trick. What's the simplest mountain you could think of? What? What's the easiest angle you could ever imagine for a mountain? 60. Oh, I was going to say 0.
Okay.
Flat. No mountain is easier than mountain. Agreed? Now think, if B is 0, isn't that a level ground problem?
Yeah.
If B equals 0, we should get the range equation from your high school physics class. I don't know if you know this, but if theta, if B equals 0, that should look like you're shooting a ball across level ground. From that, in high school physics, I know the answer is V squared over G times sine of 2 theta. Something like that. Or I know it's on page 72 near the bottom. Okay, so this is a way you could check it. I'm going to come over here and look. If we set phi equal to 0, what do you get? The phis all go away. What's cosine of phi? What's cosine of 0? 1. There's a chance where it's nice to know the unit circle, but not necessary. You can plug it in, but why? So do you agree the phis all disappear and we get 2 v squared cos theta sine theta over g, which from a trig identity at the bottom of that page, 2 sine theta cosine theta equals sine 2 theta. It works. So now, what's the point here? What we're trying to show you is that you can check hard problems against easier problems if you set the limits right. This is a fundamental trick to do, and some of you that were coding in lab know this. I said, why would you do a code that's, oh wait, none of you guys were coding. There was like one group, right? But think about it like this. If you're trying to, oh, your group was coding, right? The idea was, why would you try and get the air resistance code right if you can't get free fall right first? So first you make your code, try to do the simplest possible case. Then you add in air resistance, and then you change the parameters on air resistance and set them to 0 to verify the code still works. What we're doing here is we're saying, look, shoot this thing at some screwball angle, but make sure if you plug in the simplest possible angle, it reduces to a previous result. Enough said on that? Is that good? That's advanced checking, right? It's not just checking the units. It's a much stronger check. You're showing a complicated solution reduces to a simpler, easier problem. All right. Let's go. We got this answer now. We've got L. I'm going to go back to our first board. We got it. I'm so happy. Think. Talk to your neighbor. What should we do here? I've got to erase the other whiteboard. You start talking to each other and figure out what should we do. Go. You discuss what you should do.
This slow range equation and then try to solve for theta.
It's a
Theta, or no, P.
Good enough.
it's set it equal to a good high number.
All right. We've proved this result now. We've shown that to be true. Great. We say, well, now we're looking for what launch angle gives the maximum downslope range. Any ideas of how we might approach this? Anything?
Steeper, the hill.
What's that?
Can we find like the steepest the hill can be?
You could try and do that. Now, keep in mind, the steepest the hill could be would be at 90 degrees, and then your range would be infinite because you'd be jumping off a cliff that has no bottom. So we could do that, but it turns out that doesn't help us in this case because it creates an unreal situation. Not to mention you'd be base jumping. So you'd need a parachute and that would, yeah. Trickier question. So that's a good idea. Sometimes you can just try the biggest and smallest and see if that works. It's a good idea. It's not going to help us here because the biggest and the smallest aren't going to work out. Okay, other ideas. I mean, Venmoing your instructor $1 million is always a good idea, but sometimes that doesn't solve the problem. He needs $2 million. No ideas? The problem says requires calculus. What do you do in calculus when you look for a max? What's that? Take a derivative and set it equal to 0. That's what we're looking for. Remember that from math class? All right, okay. So now the question becomes, in a math class, it's easy, right? You just take dy dx, set it equal to 0, solve for whatever. But now we're doing physics. You have to do one more step. You have to read and understand the problem. What do we take the derivative of, and what are we taking the derivative with respect to? What do I want to maximize with respect to what? That's our goal. We're trying to maximize L with respect to theta. I know there's got to be a derivative here. dd something. What am I taking the derivative of, and what am I taking right down here? dl d theta. That's what we're looking for. Okay. Now, are you looking forward to that derivative? Does that look awful?
That's pretty simple.
It's actually, it looks like at first glance you'd be like, oh, but look, think about this. What in here is a constant? There's really only these two parts that have a theta. It's not as bad as it initially looked. Now, somebody said this, if we want to maximize this, I take this derivative, and then do I just take it, like hold it, and keep it precious and sleep with it? Well, yeah, we got to set it to 0, otherwise we're not doing anything. After you set it to 0, then what? Solve for what? Yes, excellent. That's going to give us the theta critical. That becomes theta critical. Once you know theta critical, we can get the L max or the L min. Remember that from calculus? Is this coming back now? All right, all right. So I'm going to write it out here. Ratio, go. Does anybody know a trick to speed this up? What's the first step? Do you know? When you're doing these problems, there's a trick when you get these ugly looking things. Factor out all the constants. So do that first, okay? Get out of the way. Here's why you factor out the constants first when you're doing a max-min problem. The product of these two things is equal to 0. Well, I know the first thing's not equal to 0, therefore this part equals 0. right? The constants don't equal 0. You could cross multiply by the constants and get rid of them. So said another way, you could actually just immediately go to this. If you're experienced with max and min, you don't even write the constants and you just skip right to this step. Right? You can cross multiply by all those constants or just, so a lot of times when you're writing this, you're like, wait, I could just write this, and then you can skip a step, skip all the constants. All right. Now what? What's the derivative of this? How do you do it?
U sub.
U sub is for integration.
Sorry.
I think you're thinking of what, yeah, product rule change, yeah, something like that. Yeah. So let's take the derivative of the first times the second plus the first times the derivative of the second. You know what I mean? The f prime g plus g prime f or something like that. All right, hit it. What's the derivative of cosine theta? Negative sine. Then I got to multiply by what's left. Cosine theta. What's the derivative of sine? This term. What's the derivative of that? Wait, what is it? What's the derivative of sine? Cosine of theta plus phi. But now I got to take the derivative of what's inside, right? Chain rule. But in this case, phi is a constant. What's the derivative of the constant? 0. What's the derivative of theta with respect to theta?
Just one.
1. So do you agree that all of this is just the number 1? So it looks really horrible at first. And it's like, oh, it's not too bad. Oh, wait, wasn't all of this equal to 0?
I was just about to say that.
I guess you're right, I did forget something there. Okay, so far so good? So now I'm going to rewrite. And I'm going to rewrite it in this form. I'm going to put the positive term first. Great. What are we trying to find? What was the point?
Critical theta.
We're trying to find theta. In this case, I'm going to just help us out and say a trig identity is actually going to make it easier to find theta. Look at the trig identities at the bottom of the page. We've got a cos, cos, sine, sine with a minus sign. I know this trig identity. Was it cosine or sine? I don't want to split the identity. Cosine. Now I want to explain to you carefully how this works. In particular, a lot of you might not be used to using this style of table. Notice right here, I have plus minus. Notice right here, I have minus plus. Agreed? That means if you want to use the plus sign inside the parentheses, you have to use the minus sign on this side. Similarly, if you want to use the minus sign here, you got to use the plus sign on that side. Does that make sense? So there actually is a reason you might use minus plus instead of plus minus. And this is it. So looking at this, do I want to use cosine A plus B or do I want to use cosine A minus B? Let's look up here. What is A and B here? This is A. This is B. This is A. This is B. Do I want to use the plus or minus sign here? Right. Minus. So which one do I have to use in here?
Plus.
Plus. So that just tells me I'm going to use the minus there and the plus here. Good? Well, what is A plus B in this case? 2 theta plus phi. You agree that A plus B is theta plus phi equals 2 theta plus phi. Everybody cool with that? All right. Now I'm going to run out of room. So I'm going to erase this. Everybody, do you need a second to get it? Oh, wait just a second.
It should be recorded. So
It is being recorded, but I'm just going to wait a second so people can write it down. Remember, we're trying to figure out theta. If you're just sitting there twiddling your thumbs, figure out theta. Right? If you're already done with this, yeah. Okay. Is this a good time to erase it now? Just making sure you guys had it. Just 'cause normally I would keep working sideways, but Zoom, you know what I mean? Speaking of which, I should check in and make sure it's not like all not working. Alan, still good on Zoom? I'm looking at the chat. Right on, thanks. Okay, so what was this? Did we say this all was basically cosine of 2 theta plus phi equals 0? Oh my goodness gracious. I know you want that break. We're almost there. Trust me, we're almost there. Okay, how do you solve this?
arc sine?
Arc sine?
Arc cosine.
Yeah.
Sorry.
Cosine inverse, right? We know what you meant. What's cosine inverse of 0?
And that's the top. So I think that's pi over 2.
Okay. Feeling radians tonight. I love it. How about degrees for me? 90 degrees. Is that the only one that gives a result? What's the other one that gives that? 270, right? If you weren't sure, punch it right. Cosine inverse of 0, right? It'll give you 90 degrees, but the other result is the, right? You always have to remember when you're taking inverse trig functions, there could be more than one result. You should always double check. Sort of like plus or minus sign on the square root crap of a, whenever you take square root of a number, always at least think about plus and minus. Well, we're trying to get this. So if you agree, if I rearrange this, theta should equal one of these two results. I'm going to divide everything by 2. Let's do this here. If I divide everything by 2, and then I could move this to the other side, I believe it's going to be, over here, it would be 45 degrees minus phi over 2, or 135 degrees minus phi over 2, right? Do both of these answers make sense? Why not?
The other one is upside down. I think.
Upside down?
Or well,
What is, where is, okay, let's draw some pictures here. Remember that trick? There's a cool trick you can do is set phi equal to 0 so you can get a feeling for the problem. If we set phi equal to 0, one of them is 45 degrees, the other one's this way. Right? Is this a good angle to aim to go down our ski slope? No, because if you look back at our original picture, right, our ski slope's going this way. We do not want to angle the ski slope that way. You could jump this way, but that's a totally different problem. That's not what we want. Now you could say, wait, isn't that the same thing as a mirror reflection of the mountain? Absolutely. So you could look at the mountain in a mirror, and then you could use 134, I guess, or something. I don't know. Whatever. All right, here we go. Now, in this case, that's cool. We could check this result. If you set phi to 0, isn't 45 the optimum angle for a throw? Maybe you know that from high school or something like that. So it turns out if you want to get maximum range on a flat surface, usually you think 45 degrees if air resistance is negligible. Turns out air resistance is not negligible. In baseball, they usually use like 36 degrees or 35 or something. But that's because air resistance is. What's another way we can check this? Okay, we need some numbers, huh? Plug it in. Let me do this. So here's what I need. This thing right here. Could you help me out and just take that lead brick and kick it with your foot? Like slide it. That's right. Let's see if that's about right. That's good. And then you probably want to wash your hands before you eat. You know what I'm saying? Sure. Just in case lead. Oh,
It's lead.
is it lead? Yeah, it's a giant lead brick.
It's real lead.
Oh, yeah. And one time I was working in the back and a giant shelf filled with those collapsed and fell on my foot. It was awesome. Anyways, and yet I'm still dedicated to the flip flop. I don't care, right? I paid my dues. I did all these problems. I'm wearing flip flops, damn it. All right. So here's the deal. It turns out your head is right blocking there. Can you just scoot a little bit that way? Then I need to move this table out of the way. What's up? Now, from experience, actually, Mark, you want to just come up and keep your eye? I got this earlier today at low speed, and I think it landed right here. So I want you to just I want you to stand basically right here and be ready to confirm that the ball lands right there. The angle that I'm using is about 15 degrees, okay? So what I'm telling you right now is phi equals 15 degrees. Is that showing up on Zoom? I can't go. No, it's not. Okay. All right. Somebody help me. What should theta be? He doesn't have to help. He's standing up helping me up here. Right? If B is 15, what's the optimum angle for theta? Punch it in. It's 45 minus half of that. What is that? So 37 and a half? Hopefully that's kind of showing up on Zoom. All right. So now here we go. I'm going to shoot this ball out of here. And I need to be at 37 and a half. Okay, this is 37 and a half. I don't know if you care. You guys trust me, I'm not lying to you. Okay, here we go. So just kind of watch where the ball lands. Ready? You agree it's pretty close to there? Yeah, pretty close to there. I got another one. Let's shoot. We'll let the balls roll over. All right. Now, it turns out this particular measurement is not very sensitive, it's not very sensitive. So if I change it 2 degrees this way or that, it's basically going to hit in about the same spot. So what I'm going to try to do to convince you is change it by a dramatic amount, about 10 degrees. So this is just over 45. So I guess I'm changing it by about 8 degrees. Same velocity, so try and mark. And let's do this. Here we go. Here we go. Hey, kids leaving their Play-Doh around actually comes in handy. That was approximately where it hit. Do you agree? Yeah. Somewhere in there? Okay, so now what we're trying to do is see if it hits the same spot closer or not. We're at a much steeper angle. It's about the same. Do you agree? Yeah. All right, that's what I was saying. If I keep going up, okay, at some point we see we're coming this way. Now if I go the other direction, what's the angle? 37. So I'm going to come all the way down to about 30. Right there. This will probably be about the same. A little bit closer, right? And if I go even lower, that's at 20. approximately dimensions, right? Let's give Mike a round of applause here. Go ahead and take your break. You earned that one, didn't you? Woo! That was intense. Oh my goodness. Thanks. We can move that table back and get that. You can take your break. How'd that turn out on Zoom? Could you see that at all, Alan? Or he might be taking a break. Oh yeah, okay. Hopefully you could see at least the ball hitting there for some of it. I don't know if that showed up as well. Let me see here. Yeah, it's like right at the edge. Hopefully you were able to see it a little bit. Good. Oh, man.
Try to figure out the audio problem.
I might just reboot the computer or something real quick. But yeah, you could try to diagnose it if you want. Yeah, that's cool. Yeah, let me do this really quick.
physics 110? Like, I can.
If you took physics 110 and really learned it,
Yeah,
hopefully, yeah,
I
hopefully,
got it.
right, yeah. Just,
but I took it with someone that got fired.
well, okay, so maybe that's not the best, yeah. Let's talk later. I just want to get through it. We can talk much more after class. Is that cool? It's just about time. So those of you on Zoom, give me a shot now, Alan. See if you can unmute.
Sounds good.
Yeah, boy.
There you go.
All right. What up, Linda? No. Hey, Linda, do I give tough tests or not? You got to practice, right? I think if they practice, they have a good shot at getting a good grade, but if they don't practice, they're toast. That's basically, yeah. The classic thing is the student always says, well, I get it when you do it on the board. Yeah, that's because I'm doing it, not you, right? So if you guys do it at home and you struggle with it, then you're fast, right? It's too late at that point. Yeah, watching videos is like worthless. Yeah, it's not worthless, but yeah, you just don't get it like cranking it out. Do it. See you, Linda. Peace out. I hope so. No, it's just practice and you'll be fine. Don't practice and you're in trouble, right? I keep telling them that too. Later, Linda. Okay. So that was another 3D word problem. That was a constraint. We talked about max min. I like to try and at least do one like that. There's two more types of problems that I want to talk about. I want to talk about the next type of problem I want to talk about are these equations, right? In particular, for a physicist in 3D, does anybody remember what R of t is supposed to represent? Yeah, you add all the x, the y, and the z. That x and y and z all relate to what? Distance? Position. This is the position as function of time. So the idea is you could imagine in 3D space, let's say we have x, y, and z, and you're somewhere up here. Right? You could imagine there's some in calculus class, sometimes you'll see it with these diagonal brackets, where you're talking about the location of a point in space as a function of time. And I know this, maybe you don't get the best contrast here, so I apologize. But the idea is we're going to describe a point in three-dimensional space, and then we're going to try and break it down into x, y, and z. So very quickly, you already probably know this, but we're just, because all day we're trying to talk about the independence, the idea is we're going to split this into three separates because it's easier to analyze three separate equations. So we're going to talk about x in the I hat, y in the j hat, z in the k hat. I doesn't affect j, doesn't affect k, doesn't affect I, doesn't affect j, etc. Right? Like shoot the duck. We talked about those. All these different independence of x, y motions. Right? Over and over and over, we've shown that the x motion doesn't affect the y, etc. Now, if I want to get from R of t to V of t, what do you think V of t means? Think a guess. It's the velocity, yep, as function of time. And you were already telling me, yes, good. So function of time. How do I get there, Alonzo? Of
RT.
with respect to
Time.
Yes, excellent. Nice job. Outstanding. Now, do you agree? Because these three are independent, you could take the derivative of the x separately from taking the derivative of the y, separately from taking the derivative of the z. Everybody cool with that? So basically, instead of just doing one derivative, you have to do three derivatives. Same old story. Good? And then how do we get to a of t?
The double derivative.
Yep. Or the single derivative of what?
VT.
Yep. With respect to. Yep. Or somebody else might say it this way. So far, so good. This is probably the part in calculus that you're like, finally, something that actually helped me from calculus class, right? It turns out there's a few subtle tricks in physics in reading the word problems. Go figure. When you're reading a word problem in physics, sometimes you got to carefully read. So what I'd like to do is on page 77, I'd like to look at question 4.24 together. And I just know how much space it's going to take, so I need to erase this whiteboard, okay? Yeah. Yeah, let's do that. And I'll say this one other thing. This works great for coding, but in general, we don't want to get used to this notation all the time, because if you're a mechanical engineer, or basically if you're some kind of engineer that's going to take engineering classes, we're not always going to use this, because this is only valid for what's called Cartesian coordinates. It doesn't work for spherical polar, which here's an example, right? Here's a spherical polar coordinate system. How do we specify locations on the planet Earth? Latitude and longitude, those are angles. And then we also usually specify the radius. Most places on Earth are on the surface, right? So 4,000 miles is the radius, but you know, whatever. Basically, you got to tell people latitude, longitude, and altitude, agreed? So that's basically like saying a radius and two angles. So that method does not describe, it's just not, whatever. We're going to use IJs and Ks, got it? There's a reason for that. If you don't care, I don't care. If you do care, talk to me after. Okay, I'm going to erase this. Go ahead, race ahead. 424 if you want. I'm going to do it slow. I just have to erase. And those of you on Zoom, the mic is working, so I apologize. I had a button pressed, and it wasn't the normal button. So I can hear you now if you want to shout out. Sorry about that. It's always something. I think I've had a single lecture yet where things actually all work. Again, you don't have to listen to me if you're confident in your abilities. Okay, we've got this crazy equation. Part A is an important physics. This is like the main difference from the physics problems from your math class. Okay, in this case, the question says, what units assumed on each number? Well, help me out. What units are assumed on R? What does R stand for? Position. What are the units associated with position? meters. Okay, unless otherwise specified, we're going to assume everything is in meters for a position. So now, how do I figure out the units on any of these other terms? Well, if you recall, the units of one term must be equal to the units of any other term. So I can do these terms once at a time. The units of 6 have to equal meters. Got it. Otherwise, I'd be adding somethings to not that same something. It'd be like adding apples to oranges if this wasn't true. I know that meters has to equal the units of 2t. So what are the units of 2 going to be?
Meters times seconds.
Meters over the units of t, which is meters per second. Did that make sense? Why? You got to divide by the units of time. Got it? And then how about this? And the 4 is just 4. That's the units. This is useful for checking your answers or relating these numbers to reality, right? It's sort of like in Python when you're coding something, you kind of want to know what the numbers stand for in their units. Because, right, or maybe in lab when you were doing tracker, right? There's a big difference between 100 centimeters and 100 meters. One of them fits in this room and one of them is a football field. Okay. Any questions on part A? Is that okay? Okay. In math class, they don't ever worry about units. In a physics class, we always worry about it. Part B, what is initial position? How do you do it? Don't overthink it. If you wanted to get the initial position,
Equals 0.
yeah. So now we know that initial position, that just means position at time t equals 0. So what do you get?
6 in the bottom.
6 plus 0 minus 4.
Now, if you're in a math class, they usually want you to write it like this or like this. This is physics. Usually what we do, and I checked with the engineering instructor, in engineering they're the same way, right? We don't want to write crap that's not there, right? We don't want to get in this habit. Now, if you do that, I'll tolerate it, but the engineering instructor will be pissed at you. So we would just write 6 in the I hat minus 4 in the K hat. And we would leave out the 0. Now, if you leave it in for my class, I'm not going to care. I had one student say it really helped them to see the 0 because then they don't accidentally think the K hat term is a J hat term. And I understand that. So there's a reason for that. Because this is a physics class and we know the assumed units, I might stick a unit of meters on the final result. Because we know that this is a position. So I'm going to stick in the units even though we didn't know that. That's kind of the purpose of that. So far, so good? Okay. Part C, what are we supposed to do?
Find the initial speed.
Initial speed. Any ideas? What's that? Okay. We're going to take the derivative of R of t, then what?
That t equals 0.
Okay. All right. So let's, is that it? Are we good? Should we start?
I think that's it.
What's the derivative?
It's
2 in the I hat plus 6t in the J hat. And there is no K hat.
Okay, so you said -2 in the I hat plus 6t in the J hat
Correct.
plus nothing in the K hat, so I'm not going to write it. Is everybody okay with that?
Yes.
Okay, so what did we just get?
Just -2 in the I hat.
We got the velocity. Did I ask you for the velocity? What did I ask for? Speed. So if we just do these 2 steps, I get the initial velocity. That's not what I asked for. let's just do this carefully, right? If we set t to 0, I get -2 in the I hat. I could throw on the units. What is this? The initial velocity vector. You agree it's a vector on one side because it's a vector on the other? That is not correct. You would lose points. Initial speed, we need the magnitude. You see what I'm saying? You guys know how to take the magnitude of a vector in 3D? If you have a vector like this, I'll get out of the way. If we have a vector like this, B, that's the magnitude. Sometimes you use a double line. How do we get the magnitude of a vector? Square root crap of Vx like that. Do you know what I'm saying?
Yeah.
Now, in this case, I want to point out something carefully here. When you square this and take the square root, we should think, if we're getting speed, do I need the plus minus or is it just the plus root? This is only going to be the plus because we're looking at the magnitude of the vector. That's always positive. But you should always double check and think about it. Great. When I do this, notice up here, the velocity has I hats and j hats in it. The speed does not. You see that? So what is the initial speed in this case? It's going to be 2 meters per second. And we see that minus sign makes a difference. The speed is the size of it. Is that cool? That's the other way I might try to trip you up on a test. So we see that units matter, and so do the words speed versus velocity. You know what I'm saying? All right. What's part D? Probably the acceleration, right? Okay. D. We're going to take the derivative of the velocity as a function of time, which is what?
I think that's 0.
Nope.
Just j hat.
Take a look. This is the velocity as a function of time. If you take the derivative of the initial velocity, you get 0. But if you take the velocity, if you take the derivative of the velocity as a function of time, we get 6j hat. Got it? So there's a difference, right? The initial value should be a constant, but the velocity over a function of time could change, as we see right here. Right? Remember, this was the velocity as a function of time with the derivative. It's equal to this. It's not a constant. So, but when we take the derivative, it's 6 in the j hat. Come on. So that's the trick here. And so we see some subtle things. All right. That's going to equal, I think, just 6 in the j hat. What units?
Meters?
It's acceleration.
Yeah, second square.
Good, good, good. All right. So far, so good. Now, in this case, what's the magnitude?
56 meters.
Magnitude is just 6. What's the direction?
J.
Plus j hat. Good. Or j hat. Yep. So far, so good. What's part E? Speed is a function of time. Is that right? We want speed as a function of time. We need the magnitude of the velocity as a function of time, right? In this case, do I know Vx as a function of time? It's 2, right? -2. What's Vy as a function of time? 6t. Right? It's not 6. This whole thing is what's sitting in front. So the idea is Vy as a function of time is everything that's in front of the j hat. What's Vz as a function of time? 0. Yeah, that one's 0. So in this case, we should get the square root of 4 plus 36t squared. So far, so good. Now, in this case, you might be saying, well, you should write meters per second here. I don't want to do that. This is what's called a mixed expression. We've got numbers, and we've got this parameter t. Sort of like our original definition. Notice how I didn't include the units on the original definition. The only terms that I've been showing the units are those where I've actually plugged in the number, and so I have a final number that it makes sense to put on the units because there's only numbers in the expression. If you want to learn more about that, we can discuss later. For now, I want to move on and get this problem done and get us out of this. Cool? All right. You tell it's a riveting lecture. Whatever. All right. F. Which is easier to get, displacement or distance? What's your gut tell you? Displacement. In general, what's the general technique for getting displacement? Yeah, say it again. Final minus initial. Do we know the initial position in this problem? Yes. What is R final? Do you agree that's just R as a function of t? If you give me a time, I'll get you R final, I'll get the displacement really easy. Why is distance so much harder? It might reverse direction. Outstanding. Remember when things switch around? Not to mention, this is going in 3D. In general, how could you get distance traveled? I'll give you a hint. It's a compound word, 2 words. First word, 3 letters, starts with A. Second word, I don't know, it's about 5 or 6 letters, starts with L. Calculus, how do you get the distance as you travel along the path? Starts with A. Okay.
You have to have different stages, right?
Just imagine I've got a big boat. It's filled with a bunch of animals. It's called an
Hard.
but then I want to find out how long it is. I would get the. Yeah, great. Fortunately, this is not required in class. Got it? But you remember arc length in class, somewhere in some weird calc class? That's how you would get the distance traveled. That's the length of an arc or a curve. Right? So that's a lot harder if you remember from your calc class, is it not?
I forgot about that.
Is there another way to do it? Code it. And then it's really easy. You split it into little chunks. I'm trying to sell you on this coding. I know it seems silly, but a lot of these problems, like instead of having to do really complicated words. Okay, done. I'm tired. Can you tell? All right. Okay, good. That's part G. So far, so good? Okay, so now here's the deal. How are you feeling on this problem? Good or bad? Give me a thumbs up, thumbs down. Just go with your gut. So mixing, yeah, okay. So you're probably going to need to practice the next problem. And in particular, something that we didn't do in this one. In this one, we started with position, so all we had to do was take derivatives. But if I give you the velocity, how could you get from the velocity to the position equation? You could integrate or do the opposite of a derivative. The antiderivative is an integral. One of the key differences in this class, remember that here, I want you doing definite integrals from initial to final, because the most common thing is people will integrate and forget to plug in the initial position. So I highly recommend you do 4.25 to kind of get some practice on this at home. Even if you think you're good at this, more than 95% of my students screw up at least one part in there, and I won't tell you which part, right? But students get overconfident, especially ones that think they're good at calculus. They will screw it up all the time. So, and they're like, what? I don't understand. Well, do the problem and you'll get it. But I wrote very lengthy solutions for these. That way you can check it at home. Okay. Now, all right. I need to erase the board. If you want to start looking at that one, you can and just get it started and you can finish it at home tonight. While I'm erasing the board, you can talk amongst yourselves. We got one last thing to do. So let me erase both boards. You do whatever you want, read, stretch, I don't care. Give me a second to clean up the boards here. I've got to show a simulation here. Get the simulation ready. Man, that beer is going to taste good tonight. It's been a long day. This lecture is intense, isn't it? You got globes laying around ready to trip you at any time. Got the bald spot, full display there. That's good. That's good. All right. Here we go. Imagine you take your uncle and throw him down the stairs. That's relative velocity. That's a very painful way to do relative velocity. So we're going to focus on two spheres, one red, one blue. And we're going to move them around. Before I get too ahead of myself, I want you to think about the coordinate system in this picture as being the Earth. Okay? So imagine the Earth is at rest in the universe. Okay, let's discuss that later if it is. Oh, that's cool. Oh, thanks, Angus. That's his cue. I'm like, I better shut up soon, I think. Okay, watch the screen. Ready? Imagine we have two objects moving. They're moving apart from each other. Got it? Can you guys read the numbers back there in the back of the room? Okay, so the idea here is the red one we could call object A, right? So the object is moving, A is moving in the first quadrant relative to the Earth. The Earth is at rest. You see it's at 0. Now the blue one down there is moving into the third quadrant. And that's, again, relative to the Earth, all right? I'm going to run this program again. In this case, imagine when these balls are moving around, imagine it's like we're in a drone and the drone is spying on people walking around the Santa Maria Mall or something, or a parking lot, right? These are people walking around in a parking lot. Well, in the first case, the drone was hovering above the coordinate system at rest. Imagine instead if the drone was following the red person. It would look like this. The red object stays still and the other two objects move away, right? So again, in the Earth's frame of reference, it looks like this. The drone is sitting still, they both move apart. In A's frame of reference, we see the Earth is moving away. So again, this is what it would look like on the film. If you were watching the video, it would look like all the different parking spots and cars that are parked at rest would look like they're moving because the drone is tracking person A. If you track person B, it would go the other way, right? So far, so good? So our idea here is we're going to try and get some equations that get us from this picture to that picture or that picture. Again, usually in most physics problems, we start with this understanding, but sometimes we want to understand the speed of B relative to A. Or maybe we want to understand how A moves relative to B. Case in point, air traffic control. Sometimes planes, you want to understand how fast a plane is moving towards you instead of relative to the airport, right? So is that enough to motivate that? You feel okay? It turns out there's two quick equations and we can write them down. Oh boy. Look on page, probably what? Probably the next page. What page were we on? So let's try 78.
Yep.
Start looking over page 78 while I erase the board or while I get the lights and stuff. You guys just take a minute to reflect. Yeah, that was a good one, wasn't it? There you go, Zoom. Take a minute to reflect. Got it? Good. Zoom jokes are the worst. Throwing a mask, it's like the worst jokes ever. All right, okay, so stop the share. Bad jokes. Okay, in this case, relative velocity. Sorry, I'm losing it up here. Not going to throw the uncle down the stairs. We're going to have an object A that's moving somewhere like this. We're going to have an object B moving some other way. Doesn't matter which one's which side, doesn't matter. And then to make this mesh, I think I drew this dotted line in your book. We're going to call this VAE, capital, lowercase, I don't care. So the idea is we've got these two ideas here. What do they mean? That's the velocity of A relative to Earth. That's what the A and the E means, and the order matters. Okay, hopefully this is all written down. What do you think VBE means?
Positive B relative to Earth.
Correct? You got to be careful here if you're getting lazy like me. If you get too lazy, your V's start to look like R's. So this is velocity, and this is relative, okay? Now here's what I was trying to address. It turns out we could actually discuss VEB, even though at first it feels uncomfortable and weird. This is the velocity of Earth relative to V. The idea is me walking to the right, when I walk to the right relative to the Earth, that's the same thing as saying the Earth moves beneath me to the left, right? There's no real difference in those from a velocity standpoint, right? The idea is me moving to the right relative to the Earth is the same as the Earth moving to the left relative to me. They mean the same thing. In particular, these things are related by this equation. They're equal and opposite. All right, so notice how crucial the order of the subscripts will be. If you flip the order, we're going to be off. All right. And here is what's called the velocity addition equation. What matters in these problems is we usually want to understand the velocity of A relative to B, or use that information to figure these things out. So it's crucial to understand this equation. I'm going to write it down. Give me a sec. This is one correct velocity addition equation. There are an infinite number of others. And so it gets kind of sneaky. There's a trick for knowing that you've written down a correct velocity addition equation. I like to call it the squeezed out theorem here. Look at this variable E. It comes second in the first term, first in the second term, and it gets squeezed out over here. See how it's not there anymore? This is how I remember to do it. You can do anything you want that works for you. There's many other ways to do this equation. But for me, this helps me see it. If I take the velocity of one object relative to a second, then a second relative to a third, that gives me the first relative to the third. Or set in equations, A to E plus E to B gives me A to B. So far, so good? And what looks like the difficult problem with all these simulations ends up just being a vector addition problem. So far, so good? Yes.
I just had a question. It's only negative when you're comparing the velocities in between the same.
If you switch the subscripts on one term, that's when you flip it. Which actually, in a lot of books, you'll actually see this written this way. You agree the same equation could be written VAE minus VBE. This is another correct velocity. Because take a look. I could flip the sign of this by flipping the subscripts to get this result, right? Well, you could imagine you could start flipping pairs of these all day, and flip minus signs, and you could do all kinds of different ways of flipping the orders to get this. But again, the trick is for me, when I'm writing down the vectors, all I need to know is which two add up to the third. So I look for the repeated subscript like this, where it goes AE, EV, and then I know I've written down the equation correctly. Is that good? You'd think these problems would be easy, right? They're not. Now, okay, let's look at, but not complete, let's at least start. I'm going to go straight to the hardest one. The bottom of page 79, 4.31 and a half. And I want to do this one, just set it up. We've got 3 minutes. Let's finish the setup for the problem. And by setup, I mean just literally write down the list of knowns. And what you'll see is it gets tricky to write down the knowns. We're looking at 4.31 and a half. Talk to your neighbor, finish strong here. Focus. Racing, I'll be on Zoom in a second. Still erasing. Talk. Start here. Velocity. Okay, 4.31 and a half. Some person here and there's a ball. You got this going this way. All right. I'm gonna work this. Okay, the first sentence, the train travels to the right with a speed 20 relative to the earth. What does that tell us? What variable do we know? The relative velocity, we're talking about the train relative to the earth. What do you think I would write down? VTE, capitalization doesn't matter, equals 20, not quite,
Meters per second.
not quite,
Meters per second squared. Oh,
vector,
I
I have.
sorry.
No, got, so this is crucial though. Speed and velocity are not the same. This told us to the right. And that's gonna matter. We know this velocity, not just the speed. Why am I bringing that up? What's the next one?
It's player relative to the train.
Let's see how it says speed. Okay. So what does that tell us? We're talking about the ball and the train. What subscripts am I going to use? VBT. Is it a vector or is it a scalar? Scalar. There's a big difference between, say, velocity, which has a direction, and speed. What's the next part say? What angle should player aim such that ball flies 30 degrees, what? Relative to ground. What does ground mean in this problem? Earth. So that's the word earth. You agree? So what were we told here? And what are we supposed to find? Last problem of the day, I promise. This is the last line. Let's get through it.
Didn't we do something similar earlier with velocity? We did something like velocity equals
Well, let me ask you this. What is this? Ball flies 30 degrees relative to ground. What do we know? What is that? 30 degrees. Okay, is it theta for the BT? Is it the angle of the ball relative to the train?
theta BE.
No, it's theta BE, like you said. Somebody else, I'm trying to respond to two people at once. Where'd you go? There you go. It's theta BE, not theta BT. You see what I'm saying? So this is the angle of the ball relative to the train. Wait, no, I just misspoke. There we go. That's just a cool looking thing. You see why these problems are hard? It's exactly the trouble I'm having here. If you get tired, you accidentally write the wrong angle in the wrong spot. Okay? What are we looking for? What is this? Angle player should aim is what? Theta BT. The player is linked to the train. That's what you got to look for. So notice we've got one vector in its entirety. We've got one magnitude, but we're looking for the angle. The other one, we know the angle, but we don't know the magnitude. Do you see how this problem could get nasty in a hurry? Students get lazy. They just say, well, I don't know how to do this one, so I'll stick 30 degrees up here. And I'll be like, I don't want to grade this one. I'll put a 0. I'll give you a 1 out of 5. But yeah, you're right. If you just take the wrong angle, right? So whereas if you can write this down, I would immediately give you 2 points. If you could at least write this correctly out of 5, this means a lot more to me than just doing some bullshit problem that doesn't mean anything. So it's critical to get those lists of nodes down. Not every problem, but on this one, I would probably give 2 points out of 5 for getting this information down. Isn't that crazy? It's so hard to get it right. This means more to me. Right? And then after that, it's a really hard problem to solve. Okay. I'm dead. I'm tired. Have a good night. Oh my gosh.
How'd you do back there?
Oh,
Actually, what?
it's fatiguing, isn't it?
All of a sudden, no.
If you guys want to see that code, send me an email so you could see it, and then you could see how I did it. No, that marker sucks. I just got so angry I threw it. Just throw it away. We need some more black markers.
You got my question.
What's that?
You got my question.
Which question?
Did someone?
Oh, right. Yeah. Oh my God. We could erase the board. Yeah, I'll get it if you want. You can just relax.